This is the sixth installment of Philosophy 201, Introduction to Logic. In the last session, we talked about deduction rules those are rules of inference that let you infer a sentence from previous sentences that you've already established. So we have rules such as modus ponens that lets you infer the consequent of a conditional from a conditional and its antecedent, or a rule like and elimination that lets you infer a conjunct from a conjunction. Now, it turns out that the rules of deduction by themselves are not enough. There are things that you can prove that you can't prove with all the rules of deduction. So today we need to introduce not just a new rule, but a new kind of rule. And this definitely does take us up a level of sophistication. So this will be a little bit tricky, and we'll cover just one rule today. We'll cover conditional proof. Okay, so I'll start by explaining the idea behind conditional proof in an informal example. So consider a typical sort of argument that you would, in ordinary life, you would obviously grant this kind of argument. So suppose that somebody says, if A then B, second premise, if B then C, and then the conclusion, therefore, if A then C. So it's a sort of simple transitivity of the conditional. If A then B, and if B then C, then it follows that if A then C. And that should be, I assume it is obvious, right? It's obvious that's true. For example, just to be concrete, you might say something like, imagine if you were deciding where to go to university, and imagine that somebody said to you, if you go to Princeton, then you will get a good job. And if you get a good job, then you will be happy. Therefore, if you go to Princeton, you will be happy. And you think, of course, I may not grant the premises. I may not believe that the premises were true, but if they were true, the conclusion would also be true. Okay, now the truth is, in ordinary life, we just grant that. And in fact, you might want me to just say, we'll take that as a rule. The rule, we could call it something like transitivity of conditional. However, that's against the philosophy that I've taken in this class, the philosophy I take towards logic, and that is, instead of multiplying rules, I want to get at the core, at the essence of why that kind of inference works all the time. So I want to really pin down what it is about the conditional such that those kinds of inferences are permitted. So we do have a conditional elimination rule. That is, modus ponens tells you what you may infer from a conditional. It tells you that given a conditional and its antecedent, you may infer the consequent. So now we want to ask the other kind of question, that is, how can we reason to a conditional? How can we infer a conditional? So think for a minute about what a conditional says. It says, if something, then something else. So how do you convince somebody that if something, then something else? And if you think about that for a minute, you'll realize there is actually something quite special about the way we reason to things like conditionals, and that is, it involves hypothetical thinking. So a typical kind of strategy that you might employ to convince somebody of the claim, if A, then C, for example, is you might start by saying, suppose that A. Now, if you look at the course textbook, this section we're talking about now goes under the heading of supposing. Now, to suppose is not something you might have assumed is part of logical reasoning. You might have thought logical reasoning is all about deducing, about drawing consequences. But no, what I'm going to tell you today is actually a very important part of logical reasoning is learning how to suppose things properly, draw conclusions from the suppositions you make. So let me take this example you have in front of you, and let me just illustrate informally how you might, in real life, if somebody was skeptical, how you might convince them of this conclusion, therefore, if A, then C, from the premises. Okay, so suppose that you did, as I suggested, you start here. I'll change the color just so this becomes clear what's happening here. So you say, suppose that A. Now notice, of course, that doesn't follow logically from what's come before. So on lines, the first two lines there, if A then B, if B then C, A doesn't follow from those. So you can't say, I infer A from those. But actually what we're going to do now is we're going to give you permission to suppose anything you want. That might sound like the worst possible rule of logic whatsoever. You might say, well, if I can suppose whatever I want, why don't I just suppose the conclusion? So here's the trick that we'll do to make sure that this doesn't go badly, is when you suppose something, you have to add information that you have supposed it. So imagine the following sort of scenario, this sort of fake scenario. Imagine that you're having a conversation with a person. When you enter the room with the person, you all agree on a set of assumptions. Those are like the premises of the arguments you will have with each other. But then during the conversation, you may say to the other party, you may say, suppose such and such. Now, suppose that you have to issue that person a sort of IOU. So you say, suppose that A, and the person says, okay, I'm going to mark it down that we're supposing that A. Then you continue to reason. Now, what you need to be able to do is at the end, if you're going to draw a conclusion from what went before, that is before you suppose that A, at the end, you'll have to sort of unsuppose that A. So here's how we'll do that officially. I'm going to pretend like right here where I say suppose that A, I'm going to pretend that that's, say, line N in a proof. So you're at line N. Now, what we'll do is we're going to add a new column in our proofs to the left of the original numbering of the proofs. To the left, we're going to add a column, and that is where you mark what you've supposed. So in this case, I would add a column to the left where I have N. That's the line number where I made the supposition. So I suppose that A. And actually what we'll do here is we won't actually write suppose that A, because writing that thing on the left shows that it's a supposition. It is a supposition. So actually at this stage, we just write A on the line. Now, in truth, one thing I've done here that could be quite confusing is the letter A is our justification for an assumption. Here I've had A serve as a premise. Okay. So in order to avoid that confusion, what I'm going to do right this moment is I'm going to erase the A's and B's and C's just to clarify. So I'm going to go through. I'm going to erase A's, B's, and C's, and I'm going to replace with P's and Q's. So if P, then Q, if Q, then R. Okay, now I'm going to suppose that P. Okay, same format as before, but now what I can do is on the right, I can write assumption, A, that's my assumption. And then I'm going to proceed reasoning with what I have here. Okay, so this actually, what has just happened on this line here is actually the final version of what we call the rule of assumptions. So the rule of assumptions before, we told you, if we give you assumptions, then you may, if we give you assumptions, you may write them down and you write an A on the right. That indicates they're assumptions that you made. Now you're given additional freedom. You're told you may make assumptions of your own whenever you want, as long as you do the following. You mark with on the right with an A to say it's an assumption, and on the left, you add the number of what you're assuming, and we call that the dependency number. So it depends on line N. Okay, so this line I've added to this slide is a instance of the rule of assumptions. I assume P, I write it's an assumption, and on the left, I mark. I'm in debt, so to speak. Line N, I borrowed. I'm going to have to pay it back later in some sense. So let's talk just a little bit more about how dependency numbers work. Okay, so the new format is a proof. It's just a slight modification from what we used to be doing, from what we were doing. We were just deducing. Is now there'll be a new column on the far left where we keep track of the assumptions that are in force at that stage of the proof. So let's quickly now reprove the following sequence. That is from if P then Q, and P we can derive Q. Of course, that's just modus ponens, so we'll take one step, but let's make sure we write everything out properly. So in this case, we again start with the assumption. So if P then Q, that's an assumption, but now we mark that it's dependent on itself. So every time you use the rule of assumptions, you put the thing you're assuming the number in the left, on the left. So P, that's an assumption, again, 2. Okay, now one modification of every previous rule we had, so all the rules of deducing, is whenever you deduce something from one or more lines that went before, you gather the dependencies of the things that you had on the previous line. So in this case, if I use modus ponens to write Q from 1 and 2, so modus ponens from 1 and 2, I gather the dependencies of those two lines together. So 1 and 2 get gathered down under the dependencies of 3. Okay, now just suppose, so this is a valid proof now. And in fact, the way to read that last line, so line 3, it has a very nice format now because actually line 3 tells you what you've proven. If you look at line 3, it says Q, that's what is on in the third column of line 3, is provable from the dependencies, that is 1 and 2. And that is precisely what we wanted to do. And when it says to show, it says we want to show that Q follows from if P then Q and P. That is, of course, what occurs here on lines 1 and 2. So now line 3 is a correct representation of what we wanted to prove. Let me be very clear. If you ended with, so I'm going to erase this just to show you, well, I'll just add another line here. Suppose that one ended a proof on line N, was trying to write a proof on line N, you have Q, and suppose it depended not just on 1, 2, but on something else. Let's suppose it depended on line 7, which doesn't occur here, but okay. And suppose that line 7 is something completely different. That would not be a solution to the problem you were asked to solve, the problem showing that Q follows from those two things, P arrow Q and Q, because what this shows here, this one we wrote, is that Q follows from the things 1, 2, and 7. Okay, so always now, every line of your proof, you can read it as follows. The thing in the third column is derivable from the things in the dependency list. And so you finished your proof when the thing in the third column is the thing to the right of the turnstile, and the things in the dependency list are the things to the left of the turnstile. Okay, so that's the rule now. And for all the deduction rules that we've already gone over, we just gather the dependencies of the things we're deducing from. Okay, so one more example to illustrate that. Suppose that we were on lines, say, M, and suppose that P occurred on M, and Q occurs on line N. Now, suppose that P doesn't just depend on, say, M. Suppose that P depends on some big collection of numbers. I'll just write a Greek letter here, gamma. So suppose that P depends on a long list, possibly, of things, and Q depends on another possibly long list of things. What would we do? What would we write if we now concluded P and Q from M and N and introduction? Well, what we would do is we would combine those two lists. So here my gamma comma delta is take the two lists, gamma and delta, put them together. In fact, you can erase duplicates. So if you had something like 1, 2, 2, you can erase the second 2. You just need to keep track of which things were used, which things it depended on. So this is definitely a step up in level of complexity. It seems like it's a lot of extra bookkeeping. Now we'll see why the bookkeeping is necessary. So the bookkeeping is what's going to let us do things like conditional proof. Okay, so now let's go back to the example we started with. So we want to show that if P then R follows from if P then Q and if Q then R. Okay, so now I'll set it up as before. So I'll set this up as first assumption, if P then Q. Second assumption, if Q then R. Okay. Now, in this proof, you're just going to have to trust me that this is how the rule of conditional proof works. So the rule of conditional proof says, if you derive something, one thing from something else, then you may, on a subsequent line, write if the first thing, then the second thing. It need only depend on what the second thing depended on. You can take away the dependency on the first. So that's the words make it sound much more complicated than it is in practice. I'm just going to write a proof using it to illustrate how it works. Okay. So again, what I want to show here is if P then R. So imagine we're having a conversation and I want to convince you from if P then Q and if Q then R, I want to convince you that if P then R. So I say to you, can you allow me to suppose P? And of course you say yes, because then we'll keep track of the fact that I'm supposing P by adding a 3 there. So if we use P, we'll be tracking the fact that we did suppose it. So now it does look like, if you look at the right column, it looks like 1, 2, and 3 have the same status, right? They're all assumptions. But I have to remember, when I end my proof, it's only going to depend on 1 and 2. So the P here is an auxiliary assumption. I suppose that P, and now, if ever in a proof you suppose something that wasn't given to you, you should only suppose it if you have a goal in mind. If you just suppose things for the sake of supposing, it's like taking on debts with no plan to repay them. Okay, so in this case, I'm going to write the following thing. I'll put it in blue so it's not confused for an actual part of the proof. This is a notation to remind myself, why did I suppose P? I want to convince you of if P then R. And so actually what I want to get when I suppose P is I want to get R. So I'm going to write to myself, my goal is to get R. Okay, so now once we do that, once we suppose P and say our goal is to get R, now we're back to just deducing, because if you look at lines 1, 2, and 3, it's pretty clear how you can get R from those, right? So you have a premise if P then Q on line 1, you have P, so you can get Q, and then from that end, line 2, you can get R. So you can get R from this. So now we'll just go back and do normal deducing. So we go back and say from P and P arrow Q, we get Q. So that's 1 and 3 modus ponens. Now we follow the dependency tabulation. So we tabulate together 1 and 3. Okay, now from 2 and 4, I get R. So 2 and 4 modus ponens. Okay, now I put 2 and 4 together, so I copy all their dependencies. So that's 1, 2, 3. Okay, so at this stage of the argument, I assumed P, I derived R. Now conditional proof, which is a new permission given to you. You're permitted to do the following. If from the supposition of P, you derive R, you may assert if P then R. So you may assert if P then R. Now what we're saying is from this assumption back here of P, we were able to get R. So actually it only depends on 1 and 2. It doesn't depend on the assumption of P anymore. So the if P then R doesn't depend on P. So that's the general format. So here's the lines involved are 3, 5. So 3, 5 conditional proof. So the general format is if you assume something, you prove something else, you can write in the conditional as we did here. So here's the conditional. You get to erase the dependency of the first number that occurs. So you copy down the dependencies of the second one. So in this case, 5, the dependencies of line 5, that's the conclusion of the hypothetical reasoning is line 5. You carry down those dependencies, so 1, 2, 3, but then you erase the dependency on the antecedent, that is P in this case. Okay, so this now, setting aside the blue notations, which I'll now just erase so we can see the proof as it exists in itself. So here's a correct proof that uses conditional proof and that derives if P then R from if P then Q and if Q then R. Okay, now conditional proof is a very powerful rule. There's lots of stuff now you can prove. And so in the remainder of this session, I'll just go through several examples. So the truth is there won't be anything in the remainder of this session, there won't be any new point made, but there will be lots of applications of the rule of conditional proof to individual problems. So here's a case in point. So from the assumption if P and Q then R, let's derive if P then if Q then R. Okay, so I'll begin as usual just by writing down my assumptions. So if P and Q then R, so that's my assumption here. Now, if I look at what I want to prove here, I want to prove that if P, then if Q, then R. So the conclusion that I'm trying to prove here is a conditional. The antecedent of the conditional is P. The consequent of the conditional is if Q then R. So what I want to convince you of, if I'm arguing at you from the premise, we both agree, if P and Q then R, I want to convince you if P, then if Q, then R. So I say, let us assume P. Okay, so I say, assume P. So there I added a new assumption. So that's the rule of assumptions. Now I'm going to write in blue to remind myself, why did I do that? What was I trying to prove? I'm trying to prove a conditional. I'm trying to prove if P then, if Q then R. So when I assumed P, I'm trying to get if Q then R. I'm trying to show that if Q then R follows from P. Okay, so now I'm trying to prove if Q then R. But now actually I'm also trying to prove another conditional. So I can assume Q here, that's a new assumption. And then my goal at this stage is just to get, R. Okay, so now look at 1, 2, and 3 and ask ourselves, can we get R from 1, 2, and 3? And the answer there is very obvious, right? Yes, because we want to get R, we need P and Q, the antecedent of that conditional on line 1. We have P, we have Q, lines 2, lines 3, lines 2 and 3. So let's just conjoin those on lines 2 and 3, P and Q. Now we can apply modus ponens, so we get R. So now we have R follows from 1, 2, 3. So that's 1 and 4 modus ponens. I've gotten my goal. Now, applying conditional proof like this, so conditional proof is a strategy, right? Conditional proof, sure, it is a rule, but it's a rule that must be applied strategically. You'll never just be in the middle of a proof and then suddenly say, I shouldn't say never, but the fact is very rarely will you be in the middle of a proof and just suddenly say, oh, I'm going to apply conditional proof at this stage. That would be pure luck. Usually what happens with conditional proof is you assume something, strategizing to get something else so that you can apply conditional proof. So it's a strategy. In this case, I've strategized twice. So I have sort of nested strategies here. I first of all assumed P, hoping to get if Q then R. Then since I want to get if Q then R, I assumed Q, hoping to get R. So now I need to remember why I entered into those strategies. So I've gotten my R. What should I do now? I should now remember that I was trying to get if Q then R. So I should now say, okay, good, that's what I wanted. I got R, so now I can infer if Q then R. So from lines 3 and 5, I can do a conditional proof. So 3 and 5 conditional proof. And that lets me take away the dependency of line 5 on 3. So as usual with conditional proof, I copy down the lines in which the consequent, in this case R, occurs. I copy down the dependencies, but I take away the dependency on the antecedent. In this case, the antecedent is Q, so that's dependency on 3. So now I've gotten that first goal, the goal of getting R. And the reason I wanted to get if Q then R is because I wanted to show if P, then if Q then R. So now I assumed P back on line 2. I can now write if P, then if Q, then R. So from 2 and 6, conditional proof. And now again, I copy down the dependencies of the consequent, in this case, the second line in the conditional proof, in this case, line 6. The dependencies are 1, 2, but I get to take away the dependency on the assumption of P, that's 2. So I end up with dependency just on 1. And now in this case, check this last line, double check. Is that what I wanted to prove? So is the thing on the left that is dependency on 1, is that what occurs to the left of the turnstile? So look back, 1, yes, that is what's to the left of the turnstile up here. And what's to the right of what's in the third column of the final line is what's to the right of the turnstile. So the way to read that again, of course, is line 7 says, what's to the right, this thing, P arrow, in parentheses, if Q then R, follows from what's to the left, line 1. So that's a finished proof. Okay. So next example actually is what you'd call the converse of what we just proved. So it turns out actually that these two sentences are logically equivalent. So the sentence if P then, if Q then R is logically equivalent to the sentence if, in parentheses, P and Q then R. We argued in the previous exercise from the right-hand side, from if P and Q then R to if P then, if Q then R. Now we're going to go the other way around. Okay, so again, we assume the premise, if P, then if Q, then R. So that's just our standard format for the rule of assumptions there. And now this proof is only tricky in the setup. It's not tricky in the execution. So let's look at what we want to prove. We want to prove that if P and Q, then R. So imagine a conversation again. If you want to convince somebody of if P and Q, then R, what do you assume? Or what would be a good supposition? What would be a strategic supposition? Warning, warning. Pay attention to this warning. It would not do you any good to just assume P. It also wouldn't do you any good just to assume Q. And in fact, you'll get things really garbled if you assume them separately and then conjoin them. No, you can just assume P and Q because what you're trying to show is if P and Q, then R. So I assume this. I remind myself here on the right that my goal when I do that is to get R. Okay. Now, like I said, in this problem, only the setup is difficult. Once it's set up, it goes easily because I've got a new problem now. My problem is, by that I mean, the problem has been recast by the assumption I made. And what it is now from premises 1 and 2, I just need to get R. Okay, and that's actually an easy problem because look, that's just an instance of deducing. We have P and Q, we have if P, then if Q, then R. So I'll just apply and elimination and modus ponens a couple times. So I'm going to get P from line 2 and elimination. That lets me break off the if Q, then R using modus ponens. So line 1 and 3, modus ponens. Okay, now I can get the Q out from line 2. So 2 and elimination. And that lets me get R, which was my goal. So now from 4, 5, modus ponens. Notice now this instance of modus ponens on line 6 is actually an instance where I'm supposed to collect the dependency numbers, but actually 2 gets used twice. So I have 1, 2, 2, but I can erase that duplicate. So we copy down the dependencies to the left of 4 and 5. So we just get 1 and 2. It depends on 1 and 2. Okay, so now line 7, I wanted to get R because I wanted to show that if P and Q, then R. So now I've done that. I've gotten R from P and Q. So from 2 and 6, conditional proof. Now let's double check. Do we know how to do the dependencies for conditional proof? What do? We take the second line, 6, we get its dependencies, we copy them down, we copy down the dependencies 1, 2, but then we can take away this dependency. If it occurs, it does occur, so I can cross off the 2 here. So it just depends on 1, which is good because that's what I wanted to prove. What I wanted to prove was if P and Q in parentheses then R, that follows from if P then, if Q then R. Okay, so one more fairly straightforward example of conditional proof. So, but this actually turns out to be a very powerful application of the rule that you'll end up using probably quite frequently. So this sequent here at the top is called contraposition. So it says that if P arrow Q, then if P then Q, then if not Q, then not P. Okay, so conditional can be flipped with negations added on the antecedent and consequent. So again, you might think that should just be a rule, but we can prove it from the rules we already have. So no need to add a new rule. Okay, so let's think how we'll do that. Well, we are trying to prove a conditional. So why don't we assume the antecedent of the conditional? So assume not Q, the antecedent of the conditional we're trying to prove. Our goal is to get not P. That's going to be easy because modus tollens tells us from P arrow Q and not Q, we get not P. So 1, 2, modus tollens. Now the proof is not done, of course, because what we want is if not Q, then not P. So now remember that when we assume not Q on line 2, we meant to get not P, so we could do this. So 2, 3, conditional proof. And again, we copy down the dependencies of the second line, that is line 3. We erase the dependencies if they occur there of the assumption, in this case, line 2. So that just leaves us with 1, which is what we wanted. We wanted to show that this thing on the last line follows from the thing on the first line, if P then Q. Okay. The last one was a powerful result, not too hard to prove, but very powerful. The next one here, at first, might look very funny because what we have here actually is a case of, this is a case of something where there's nothing to the left of the turnstile, which might seem impossible. How can you derive something with no premises, which is what this says? This says from no premises, you get if P, then P. Okay. Now, if we didn't have conditional proof, obviously that would be impossible because every rule we had before conditional proof, it grew the number of dependencies. So every rule before, you would increase dependencies. There was no way to reduce dependencies. However, with conditional proof, you can take away dependencies. And so in theory, you can take them away until there's no more dependencies left. So this is a very simple case of that here with this tautology, if P, then P. So assume P. Now, our rules always must be taken literally. And if sometimes it's not clear what their literal meaning is, then you should ask. So if you don't understand, so our rules are better than the US Constitution. Our rules are better than the US IRS tax code. That is, our rules don't have loopholes. Our rules actually are completely precise. There's no case you can bring to us where we're going to scratch our head and say, we're not sure whether the rule applies or not. They are 100% non-ambiguous, these rules. Now, I haven't always been 100% non-ambiguous in describing the rules to you. So one thing that might not be clear from what I've said to this point is when I say with conditional proof, you take an assumption and then another line, and you're allowed to write the conditional that starts with the assumption as antecedent and the other line as consequent. When I said other line, do I permit that they're the same line? And the answer in this case is yes. So conditional proof can be applied where both lines are the same, both the assumption and the thing gotten from the assumption, because you didn't move at all. It's just a duplicate. So in this case, it is permitted on line 2 to write if P then P, one conditional proof. So you used one twice. You used it both as the assumption and as the thing derived from the assumption. But now the tricky part about this is let's think about the dependency numbers. The dependency numbers, it says, the rule for conditional proof says, you take the dependencies from the second thing, that is what corresponds to the consequent of the conditional, you copy them down. So here we're going to do that, copy down the dependencies of line 1, which are line 1. But then we get to take away the dependencies of the assumption. Now, in this case, the assumption is the same as the thing we derived. So that's 1. So we actually get to erase that 1. That leaves us nothing. If it makes you happier, you can write with this blank spot on the left, you could write a dash to show there's nothing there. You could write an empty set symbol or something, but you can just leave it blank. There just are no dependencies. So what this says, line 2, is if P then P follows from nothing. It follows from anything. It just is true. It just is provable. Okay, so this is the first example of something that can be proven from no premises at all. So it's a tautology. Okay. The last couple examples I'm going to give in this session are actually not hard to prove, but they help, first of all, they help clarify what you can and can't do with the rules. And the second thing is these are actually examples of what some people call a paradox. So some people think this example that I'm getting ready to show you here is a little bit fishy, that actually shows that maybe something's wrong with our system. I'm not going to take the time here to explain why they're wrong, why actually nothing's wrong with our system. But to know that you can prove this will be a very useful thing as we go forward. So what we're going to show here is that from the assumption that P, it follows that if Q, then P. Okay, and of course, if you think about that for a minute, you'll see why some people think that's paradoxical. It seems a bit strange that from P alone, you can show that if Q, then P, because Q may have nothing to do with P. Okay, so how do we actually prove that? So we have, as usual, our assumption of P, because that's what's to the left of the turnstile. So that's what's assumed for the problem. Now we want to show that if Q, then P. So typical strategy, right, is we assume Q with the goal, assume the antecedent with the goal of getting the consequence. So the goal here is to get P. But now actually we have P already. We have P on line 1. And you might think, well, that's not, but that we can't use conditional proof, because conditional proof says if you assume something and then get something else, then you can apply conditional proof. But actually the letter of the law, what conditional proof says is if you assume something and you have something else, it doesn't have to come later. It could already be there. So that might sound like it's too good to be true, or it might sound like cheating. But in this case, it's perfectly legitimate on line 3 to now write if Q, then P. Okay, so that's from 2, 1. So you see here now, the numbers seem backwards from what they should be because the assumption came after, the assumption of Q came after P. But that is legitimate. And now what are the dependencies? So if you look here, again, we take the dependencies of what occurs second, that is line 1. So we take dependency on 1. And now we can erase dependency 2 if it occurred there, but it doesn't. So this just depends on 1. So that finishes the proof, because now if Q, then P, we've shown follows from just P alone. Okay, this result actually is sometimes called positive paradox. And you'll see why it's called positive paradox in just a minute as we look at one called negative paradox. And so the idea that's paradoxical is the idea is just that from P, you can infer that if something else that might not be relevant to P at all, then P. Okay. So this next one here is negative paradox. And actually, it's even more surprising than positive paradox. Negative paradox says if you assume not P, then the conditional if P, then Q follows. No matter what Q is, Q can be anything whatsoever. As long as not P, then if P, then Q. Okay, now instead of going to the philosophy of why that's the case, or arguing about why this is not a problem, I'm just going to explain to you how you can prove this, because I think you'll find that you'll use it very frequently in arguments once you see how to do it. So assume not P, that's your assumption. Now we want to show that if P, then Q. Normally, a good strategy for showing if P, then Q is assume P and try to get Q. In this case, I'm going to recommend something slightly different. Okay, so let me just give a little hint about another strategy in this case. Is if you think about it, we saw a little while ago that if P, then Q, from if P, then Q, you can derive if not Q, then not P. So that's contrapositive. So if P, then Q gives you if not Q, then not P. And in fact, those two are equivalent. From one, you can get the other, and vice versa. So actually, this problem to show that if from not P, you can get if P, then Q, is in essence the same as from not P getting if not Q, then not P. Okay, so the thing on the right here, the P arrow Q is the same, equivalent to not Q arrow not P. So what I'm going to do is I'm going to derive that, and then I'm going to basically apply contrapositive and get P arrow Q. Now, so I'm going to first try to get this here, not Q arrow not P, and then I'll do contrapositive. But that actually, the first goal, getting not, if not Q, then not P, is what we just did. That's positive paradox. So I'll just repeat it. I'll just do the same thing again with the different letters. So I'll assume not Q. So I assume that on line 2. Then I apply conditional proof. So I get not Q, arrow not P. That's 2, 1 conditional proof. And again, this depends just on 1. Okay, so that was my temporary goal. And now I'm going to do a contrapositive maneuver. So what I'm going to do now is I'm going to assume P, because from line 3, I'm going to get if P then Q. So I'm just going to do contrapositive to 3. So what I'll do is assume P. Now, I want to be careful, right? So it's not true that you can apply modus tollens to lines 3 and 4, but you can change P into not P. So line 4, double negation. And then you can apply modus tollens to 3 and 5 to get not Q. And then take off the double negation. So 6 double negation. Again, just copying. So double negation is another one of those deducing rules. So you just carry down the dependencies. And then finally, from 4 to 7 gives me what I wanted, if P then Q. So 4 to 7, conditional proof. The rule of conditional proof says take the dependencies of the second one, that is line 7 in this case, copy them down, and then erase the dependencies of the first one. If it occurs, it does, in this case, line 4. So we just get 1, which is what we wanted. We wanted from the assumption of not P to get if P, then Q. Okay, so those are some examples of how you can use conditional proof. The truth is, with the deducing rules we have already and conditional proof, you can prove many things. It's a very powerful system already. In the next sessions, we'll do the remaining rules that involve making suppositions and deriving things. So we'll do the rules of or elimination and reductio ad absurdum.